We are in section 2.6, Implicit Differentiation and Related Rates. This section is pretty heavy. The topics that are discussed here are really important, and make sure to ask if you have any questions. So first thing is, it says remember that ddx is an operator that instructs you to take the derivative and treat x as the variable, whereas dy is an operator that instructs you to take the derivative and treat y as the variable. So the example right below says find the following. It says part A, d dy of 3y squared. This is just the normal derivative since it's asking us to take the derivative with respect to y, and all I have in this problem is y's as my variable. So doing that, I would use the power rule and get 6y, whereas multiplying that exponent to the coefficient out in front and then subtracting 1 from that exponent. Likewise, for part B, it says d dx of 3x squared. And this time I have x's, and I'm asking to take the derivative with respect to x, so the same thing. So 2 times 3 is 6, and subtracting 1 from my power, I have just 6x. The next one, though, is where we get a little different. This time it's asking us to take the derivative with respect to x. However, we have 3y squared. We don't actually have x's in this problem. And so the first thing I'm going to do is take the derivative of this, and we don't know if y is a function of x. We don't know what y is, and so we're going to go ahead and say this is going to equal 6y, just like how we did before. However, the thing that I need to take into consideration is the possibility of the derivative of y with respect to x. And so we're going to try again for part D. This time it's asking us to take the derivative with respect to y, so d dy, but we don't have y's, we have x's this time. And so taking the derivative of 3x squared, we get 6x times, and we have to take the derivative of x with respect to y. So new part here is to look at these, and when we have dy dx or dx dy, would be when I'm taking the derivative of a different variable with respect to x or with respect to y. Right below this we have what's called explicit functions, and an explicit function is a function in which the dependent variable can be written explicitly in terms of the independent variable. For example, y equals f of x. So for example, we have y equals 3x squared minus 2x plus 1 as an example of an explicit function. What this means is we can solve for y. Or not necessarily y, it could be a different variable, but you can isolate one of the variables. Where on the next page we have what's called implicit functions or relations. And this is a function or relation in which the dependent variable is not isolated on one side of the equation. So we have, for example, the equation x squared plus y squared equals 1 represents an implicit function, specifically a circle. So if you notice on this one, I don't have one of my variables isolated. So the example down below says given 2x squared plus y squared equals 4. Find dy dx. And so we have a couple different things here. First thing is technically you could solve this for y, and that's the note that's down here at the bottom. But I'm going to leave it as this form and take the derivative. And so since it's asking us to find the derivative, it's asking for us to find dy dx, it's asking for the derivative with respect to x. So derivative with respect to x. So that means whenever you take the derivative of an x term that just has x's as my variable, it's just normal, like what we've been doing before in the class. When I have a different variable and I need to take the derivative with respect to x, then that's when we're using that idea of that implicit differentiation. So first term we have is 2x squared, so it just has x's, so we're going to have 4x using that power rule, plus, now taking the derivative of the second term, we have 2y as my derivative, but times, and I'm taking the dy dx, the derivative of y with respect to x, equals, and then the other side of the equation is just 4, and the derivative of 4 would just be 0. So it did ask for us to find dy dx, so I need to isolate dy dx. So I'm going to go ahead and subtract 4x, and then the next thing I'll do is divide by 2y. So I have dy dx is equal to negative 2x over y, and you would get that by, again, dividing both of these sides by 2y and simplifying it. So this is our derivative. And then also it says at the bottom, note that we can solve this implicit equation for y and arrive at two explicit functions. You get y equals plus or minus the square root of 4 minus 2x squared. And you get that again by solving for y in the given problem, the top and bottom of the unit circle respectively. It says, however, some equations cannot be easily written as one or more explicit functions. Thus, we need to use this method of what's called implicit differentiation, which is what we used up above. So again, this implicit differentiation idea is what we used up here to solve for this derivative. But for this problem, you could isolate y, and if you did that, you'll notice that we have y equals plus or minus the square root of 4 minus 2x squared. To take the derivative of this, I would have to use the power rule, and I would also have to use the chain rule. And doing that, I have plus or minus 1/2 times the inside function, which is 4 minus 2x squared raised to the negative 1/2 by subtracting 1 from the exponent, times the derivative of the inside, which would be just negative 4x. And then rewriting it, I have negative 2x over plus or minus the square root of 4 minus 2x squared. And then you can see that this plus or minus the square root of 4 minus 2x squared is equal to what we have for y. And we arrive at this as our derivative, which matches what we had up above. So two different ways to actually find the derivative dy dx for this problem. One's using implicit differentiation, and one is just using our regular taking a derivative as we've done before. So the next example that we have says, let the equation of the function be x squared plus xy plus y squared equals 3. Find all points on the graph of the equation x squared plus xy plus y squared equals 3 that has horizontal tangents. So again, remember that horizontal tangents meant that we have our derivative dy dx would be equal to 0. The slope would be 0 when we have horizontal tangents. So in order to do this, the first thing we need to do is take a derivative. If you notice, this time for this equation, I am unable to isolate y. So I do have to use that implicit differentiation. So taking the derivative with respect to x, like it says dy dx, that first term is just going to become 2x plus, now the second term, because I'm multiplying two variables together, I do have to use the product rule. So my first term would be x, my second term would be y. So the product rule works by doing the first one times the derivative of the second. The derivative of y would just be 1. But then you have to do dy dx plus the second one, which is y, times the derivative of x, which is just 1. I'll put that down again, you don't need to. Plus the derivative of y squared would be 2y times dy dx equals, and the derivative of 3 is just 0. From here, we need to isolate our dy dx, which is actually in two terms. So what I'm going to first do is go ahead and move the 2x and the y that we have that do not have a dy dx to the other side. So I have dy dx times x plus 2y times dy dx equals, and then negative 2x minus y. From here, I'm going to factor out a dy dx on my left side. So I have dy dx times x plus 2y equals negative 2x minus y, and then divide both sides by x plus 2y to isolate my derivative, or my dy dx. And so this would be my derivative here, and I need to figure out where this is equal to 0, since we're asking not just for the derivative, but finding these horizontal tangents. So I'm going to go ahead and set this equal to 0. And from this, I can multiply both sides by the denominator. And doing that, I have just negative 2x minus y equals 0. And from here, I can solve this, and I get negative y is equal to positive 2x, or we get y equals negative 2x. And it doesn't tell me an answer. I still have to be able to solve this. So I'm going to go ahead and substitute this back into that original function, which is x squared plus xy plus y squared equals 3. So instead of all the y's, I'm going to write negative 2x. And so we have x squared plus x times negative 2x plus negative 2x squared equals 3. And again, that's just substituting it into the original problem that we had. From here, I'm going to clean this up. We have x squared minus 2x squared plus 4x squared equals 3. Combining those terms on the left, we get 3x squared equals 3, or x squared equals 1, or x equals plus or minus 1. And so we have now two ordered pairs. I have when x is equal to positive 1 and x is equal to negative 1. And so I need to find those y values. And we do know that our easiest equation here to look at is that y is equal to negative 2x. And so when x is equal to positive 1, y is going to be equal to negative 2. And when x is equal to negative 1 times negative 2 would be y is equal to positive 2. So the 2 points, because it does ask for points in this problem, are going to be at 1 comma negative 2 and negative 1 comma positive 2. So part B says find the equation of the tangent line through the point 1, 1. So this time we want the equation of the tangent line. So in order to do that, I need to first find my slope at that point, and the slope is equal to that derivative at the given point. And so our derivative from up above is negative 2x minus y over x plus 2y. And we're going to evaluate this at this point that we were given, which is going to be at 1 comma 1. So I'll put down x comma y is equal to 1 comma 1. So every time we see an x or a y, we put a 1. And so this works out to be negative 2 times 1 minus 1 over 1 plus 2 times 1. So the numerator is a negative 2 minus 1, or negative 3, over 1 plus 2, and the denominator 3. So our slope at point 1, 1 is going to be equal to negative 1. And then to find the equation, I'm going to use y minus y1 equals m times x minus x1, our point slope formula. And substituting in x1 and y1, and my slope that I just found, we have y minus 1 equals m, which is negative 1, times x minus 1. And then I'm going to distribute through my negative 1 for my slope. And then isolating y, we arrive at y equals negative x, adding 1 on both sides, plus 2. And this would be the equation of the tangent line that passes through point 1, 1 for this curve that we have up above of x squared plus xy plus y squared equals 3. The next example, I'm going to go ahead and circle, and we'll look at that one together in class. And then it switches topics, and we start talking about related rates, which is another big topic for this class. So it says when blowing up a balloon, both the volume and the radius of the balloon are increasing, and the rates of increases relate to one another. It is much easier to measure the rate of increase of the volume than it is to measure the rate of increase of the radius. In this section, we introduce the idea of related rate problems, which involve computing the rate of change of one quantity in terms of the rate of change of another quantity, which may be easier to measure. So note, remember that rates of changes are derivatives. We have some strategies for solving related rate problems. One says to read the problem carefully at least twice. So as we go through these, make sure to read the problem again a second time. 2 says assign variables to all quantities that are changing. So anything that's changing is a variable. So it changes with time. Make sure that you're labeling that as a variable. And label all constants in the equation. Write the givens and the wants in mathematical notation. So these are likely going to be rates. And remember, again, rates are derivatives of the form. It depends on what variables you're describing. So maybe it's with respect to time, so use dt. Maybe it's talking about height, so use dh, and etc., depending on how you label it. So at a particular moment in time, and or constants like x, q, or p. 4 says to write a general primary equation that relates the constants and variables to the problem. In some cases, this is given. Other ones, it might be like a geometric formula or an economic formula, such as profit equals revenue minus cost. But other times it will be given to you. 5 says if any quantity in the equation is constant, you may replace that variable with a numerical value. If any quantity in the equation changes throughout the problem, leave it as a variable. 6 says use the chain rule and implicit differentiation, so what we just talked about just a moment ago, to differentiate both sides of the equation with respect to, and our big thing is we're taking the derivative with respect to time for all these problems. And it says substitute the given data and solve for the unknown quantity or rate desired. 8 says include appropriate units and make sure your answer makes sense. So make sure you check to make sure you're using the appropriate units and that your answer does make sense. So do that common sense check. So the example says the manager of a company determines that when Q100 units of a particular commodity are produced, the total cost of production is $1,000, where C squared minus 3Q cubed equals 4,275. When 1,500 units are being produced, the level of production increases at a rate of 20 units per week. What is the total cost at this time, and what rate is it changing? The first thing to note is that it says Q100 units, and so down below it says the level of production is increasing at a rate of 20 units per week. So now the issue is that this is in units, however it needs to be in hundreds of units, and so this is the same thing as saying 0.20 100 units per week. And then likewise it does say when 1,500 units are being produced. So again, since we're dealing with this idea of Q100 units, this is the same as just 15, and I'll say 100 units. So making sure those units match up. And so the first one that we discussed on here says a rate. And so this is talking about units, which they said is Q. And so I'm going to go ahead and say Q equals units. And I'll put down hundreds of units here too. And then we also have not just units, but it's also talking about the total cost. And so I'm going to go ahead and let C equal cost. And then T is going to be our time, and we're measuring time in weeks. So I'm going to say T equals time. And again, I'll put down weeks. For all the problems, they're going to be different. Sometimes it's annually, sometimes it's daily, weekly, monthly. So make sure you take a note of what they're measuring time with. And so the first thing that we have here is the rate of 0.200 units per week that we just wrote down. And since it's a rate, we're going to write that as a derivative. And since Q is what we're using for units and T is what we're using for time, this is going to be EQ dt, which is equal to 0.20. And it's asking for us what is the total cost at this time and what rate is it changing. So it wants to know the total cost at this time and the rate that it's changing. So I'm going to say find that cost that it's changing, so dc dt with respect to time, when we have Q, our units, is equal to 15. So we know that Q is equal to 15, and so I'm going to go ahead and write down the formula that this time it was given to us. So we do have C squared minus 3Q to the third equals 4,275. And so from here we're going to take derivative with respect to time. And so we're going to have 2C times dc dt minus, and then we have 3 times 3, which is 9, q squared times dq dt equals, and then the derivative of that constant would just be 0 on the right side. And so from here, we're asked to find dc dt. I'm given dq dt, and I'm given q. We do have an issue because we do not know c. And so in order to find c, I'm actually going to be using my original equation that was given to me and substitute in q is equal to 15. And so we have c squared minus 3q to the third equals 4275. And so I know that q is equal to 15 cubed equals 4275. And then solving this for c, and remember c is cost, cannot be negative here, and so we get 120. And so I'm going to substitute in 120 for c. I'm going to substitute in 15 for q, and dc dt is what we do not know. And our dq dt is equal to 0.20. And so from here we're able to solve this for dc dt since it's the only thing that we don't know. So from here we get 240 dc dt minus 405 equals 0. I'm going to add 405 to one side and divide by the 240. So we have dc dt is equal to 405 over 240. And dividing this out, we get this is equal to 1.6875. And again, we need units. And so this is in cost per time since it's dc dt. So our cost is going to be, and we measure things in C. If you look up above, it's in thousands of dollars. So $1,000. And we're going to say per week. And so at this level of production, total cost is increasing at and it's $1,687,500. I'm just going to multiply by the 1,000 or move my decimal place 3 times to the right, and so this works out to being $1,687.50 per week. The next example I'm going to go ahead and circle, and we're going to look at this one together in class.